before we solve this exercise, let us address the problem that we encountered yesterday. We were unable to solve that exercise 20, where we were asked to find the units in this ring, that is the ring of 2 by 2 matrices with integer entries. Later I thought about it and it's not that difficult. My guess was correct. Namely, the matrices that will be units in this ring, that is the matrices which will have multiplicative inverses in this ring, are the ones having determinant either 1 or -1. Let's see why. Suppose A is a matrix in this ring. Then A is a 2 by 2 matrix with integer entries. So determinant of A will be an integer. Now if we are assuming that this is a unit, that is if A has a multiplicative inverse in this ring, then its inverse is also going to be an integer matrix. And from the properties of determinants, this has to be the reciprocal of the determinant of A. And this of course is possible only when A is invertible, and hence equivalently this is non-zero. Now additionally, because things are happening here, so determinant of A is a non-zero integer, and because A inverse belongs to this ring again, so determinant of A inverse is also an integer. So that means 1 over determinant of A must be an integer, and that is possible in only one case, when this is either 1 or -1. So the set of units in this ring is the set of matrices for which this is +1 or -1. So that is the description of the elements in this ring which have multiplicative inverses. Okay, let us now start our group theory exercises. For any group G, prove that the commutator subgroup is a characteristic subgroup of G. Recall the definition of a characteristic subgroup. A subgroup H of G is called a characteristic subgroup of G if the image of H under any automorphism of G is again contained in H. For all automorphisms T of G. Now we have to prove that if you have the commutator subgroup of G in place of H, then these things happen. Now note that since the commutator subgroup is generated by the commutators of the group, so it's enough to prove that if you say take two arbitrary elements x and y in G, then the image of this commutator under any automorphism of G is again here in the commutator subgroup, because then since these elements generate G prime, so if you apply any automorphism on any element of G prime, automatically all those images will be in G prime. So we start the solution like that. It's enough to show that for any elements x and y in G and any automorphism T of G, x, y, x inverse, y inverse, T belongs to G prime. But this is clearly true because x, y, x inverse, y inverse, T, using the fact that T is a homomorphism, can be written as xt, yt, xt inverse, yt inverse. Now note carefully that this again is a commutator of these two elements xt and yt, which are again elements in our original group G. So this belongs to G prime. So that's just it. It shows that the commutator or the derived subgroup of any group is a characteristic group. Next, exercise 9. If G is a group in a normal subgroup of G, and M a characteristic subgroup of N, not G, okay, characteristic subgroup of N, then prove that M is a normal subgroup of G. Okay, so now we have a group G and a normal subgroup N of G, and M is a subgroup of N, that is a characteristic subgroup of N, then we have to prove that M is a normal subgroup of G. Okay. Let G belonging to G be any element define Tg a mapping from N into itself by this formula. Ntg is G inverse Ng. Okay, so the element G we are choosing from the original group G. However, we are saying that this Tg is a mapping from N into N, where the image of N, which is small n, is any element of capital N, under Tg is G inverse Ng. Note that because capital N is normal in G, so this G inverse Ng will be an element in capital N. And clearly, for a given N, G inverse Ng is unique. So we write all of that at once like this. Note that Tg is well defined because N is normal in G. For any two elements N1 and N2 belonging to N, we have N1, N2 Tg equal to G inverse N1, N2 G, and that is equal to, and this can be written as, we have already gone through this type of manipulations in that place where we did some calculations involving the inner automorphism group. There we have seen these things, but not exactly the same things. Note one thing, that we may mistake Tg for an inner automorphism of N. That is not true. Tg is not an inner automorphism of N. Although it looks like an inner automorphism, but it is not. For that to happen, this G should come from N itself, which is not necessarily true. G is an arbitrary element of G. So small g may as well have come from outside of N. So that's why we are repeating all the things essentially. Anyway, so we have now this, and this one is N1 Tg, and this one is N2 Tg. Thus, this is a homomorphism of N for any n belonging to the kernel of Tg, we have what? Uh, then n will be mapped onto the identity element of capital N by Tg. That means this. By the cancellation laws in G, we have E equal to N, because E is equal to G inverse Ng. So E can also be written as G inverse Eg. So you can cancel G inverse and G from both sides using the cancellation laws. Thus, the kernel of Tg consists of only the identity element, which implies Tg is one-to-one. Tg is injective. Next, for any element nu belonging to N, there exists G nu G inverse belonging to N such that G nu G inverse Tg is G inverse G nu G inverse G. This is equal to nu. Note that for nu belonging to N, this again belongs to N because N is normal in G and its Tg image is nothing but nu. So any element in N appears as the image of some element in N under Tg. So Tg is surjective or onto. We have thus shown that Tg is a homomorphism which is one-to-one and it's onto. That means it's an automorphism of which group? N. So this is an automorphism of N. Since M is given to be a characteristic subgroup of N, G inverse Mg, which is the Tg image of M, is contained in M itself. Now let's look at this final inclusion. G inverse Mg is contained in M, and this is true for any G belonging to G. So this just tells us that M is normal in G, since the element small g is arbitrary, M is normal in G. So this completes the solution. Ten. Let G be a finite group T an automorphism of G with the property that xt is equal to x for x belonging to G if and only if x is equal to E. Prove that every element G in G can be represented as G equal to x inverse xt for some x belonging to G. Okay, so we are now in a finite group G which has an automorphism T that maps an element into itself if and only if that element is the identity, which means that this automorphism fixes only the identity, it changes everything else. No element in the group other than the identity is kept the same by the map T. If this happens, then we have to prove that every element G can be represented in this form for some element x in G. Let us consider a set H, which is the set of all elements in our group of this form. Okay. Now if x and y are elements in G, such that x inverse xt is equal to y inverse yt, then okay, so what do we get from this equation? If we multiply on both sides from the left by x, not x inverse, by x, then on the left side we will have xt, because x and x inverse will cancel each other, and on the right hand side we have x y inverse yt, or now from here if we multiply both sides of this equation from the right by yt inverse, then we get this. Or now because T is a homomorphism, this left hand side is nothing but x y inverse T, and the right hand side of course is x y inverse. So that means x y inverse is a group element which is not changed by T, but according to our hypothesis the only such element is the identity, so that means x y inverse must be the identity. By the given condition on T, we must have this or x equal to y. So here what we have shown is that for two group elements, the corresponding elements in H, if they are equal, then the original elements chosen from the group must themselves be equal, that is, they must be the same element. Equivalently, if x and y are distinctly chosen from the group G, then this one and this one must be different. That is our conclusion. This means that for distinct elements, say A and B in G, A inverse AT is not equal to B inverse BT. Now if one wants, one can use the language of functions to make it somewhat more rigorous. What I am now going to conclude from this analysis is that um, there are at least as many elements in H as there are in G, because you have G like this and here you have H. You are taking an element A, you can make that element correspond to this. You are taking another element B that is different from A, corresponding to that you are getting this element, and these two are not equal. That's what we have shown. So there are at least as many elements in H as there are in G. That is, however, H is clearly a subset of G. So that's why at the same time this is also the thing. So they must be equal. And since H is a subset of G, equality of their cardinalities will imply that the sets themselves are equal. Now what I was saying here is that one can now set up a function from G into H that maps an element A onto this element. The function will be clearly well defined, and what we have shown here is that the function is one-to-one. So that's why from the one-to-oneness of that function we get this inequality. But since we have actually understood what's going on inside, why we are getting this inequality, so I don't think there is any need to bring the language of function into this. We can just simply write like how we explain this right now. So there are at least as many elements in H as there are in G. That is, this. But we already know that the other inequality is also true. Hence, since H is actually a subset of G, this implies H must be equal to G. So H must be equal to G means we have what we want. That is, any element in G will also be here and so will be expressible in that form. Thus, every G belonging to G can be written as for some element X in G. Then 11. Also, this one also starts like the previous one. Again, let G be a finite group. T an automorphism of G. With the property, same property, that xt is equal to x for x belonging to G. Okay, that is understood, that's not written here. If and only if x is the identity element. Suppose further that T square is the identity automorphism. Prove that G must be abelian. Okay. So although the starting is just like the previous exercise, but there is an additional hypothesis on T now, namely the square of T is the identity automorphism. We now have to prove that the group must be abelian. Okay, in this case, the solution proceeds like this. Let G belonging to G be any element, and let us denote the image of G under T by H. Okay, H means GT. By the previous exercise, so B can now use the result of the previous exercise directly. G being an element in G, and since there is one such T, can be written in this form: K inverse KT for some element K in G. Then or now we calculate, should we calculate GH or H? It does not matter, any one of it we can calculate. Let us calculate GH. GH will be what? K inverse KT and H is GT, on this we are again applying T, and this is equal to, this of course we keep as it is, in this second part, because T is a homomorphism, so we will have K inverse T times KT T. Okay, now this is, I think this calculation would look much better if we write the things in the middle. Now K inverse T is nothing but KT inverse. Simple properties of a homomorphism. And here we have KT square. T square is the identity automorphism. So these two things give us the identity element in the group, and Ki is K, so this is equal to E. So GH is E, hence H is actually G inverse. So that means any element G, note that G was arbitrarily chosen from the group, any element G gets mapped by T onto its inverse, nothing else. Now for any elements G1 and G2 in G, we have G1 G2 T equal to, by what we have just now proved, it is the inverse of G1 G2. And we know that in any group this thing is the same as G2 inverse, G1 inverse, but G2 inverse is G2T and G1 inverse is G1T. Because T is a homomorphism, the last thing is equal to G2 G1T. Now we are going to use the fact that T is one-to-one because it's an automorphism. Since T is 1 to 1, this implies that the inputs must also be equal, that is G1 G2 is equal to G2 G1. So that means any two elements in the group commute with each other. So G is abelian. Then 12. This is a starred one. Let G be a finite group and suppose the automorphism T of G, there is some automorphism T of G that sends, just give me a moment, that sends 3/4 of the elements of G onto their inverses. Or not just 3/4 but more than 3/4. Of the elements of G onto their inverses. Prove that T actually sends all the elements onto their inverses for all x belonging to G and that G is abelian. In the beginning itself, we assume without losing generality that G is not the trivial group consisting of a single element, because that group we already know is abelian and it has exactly one automorphism, that is the identity automorphism, which sends the single element to itself and hence it sends that element to its own inverse. So all the things are true for this particular group. So we can assume without losing much generality that G is not the trivial group. Now we are now going to consider a set H. It consists of those elements of the group that are not mapped by T onto their inverses. That is, xt is not equal to x inverse. We don't really know what this set is. This set may very well be empty. In fact, we ultimately have to show that this set is empty, because we want no element of G to behave like this. We want to show that for every element x in G, this is the case. So, but that's something we have to show. So before showing that, we don't really know. There may be some elements in H. But now what is given? It is given that T sends more than 3/4 of the elements of G onto their inverses. It is given now what is the set of elements in G that are mapped by T onto their inverses? Clearly they are the ones which are not in H. They are mapped by T onto their inverses. So that set is G minus H. I mean G difference H. It is given that the size of this set is at least 3/4 of the order of G. That means this. Hence, what do we get from the, what can we say about the order of H itself from here? You can of course solve this inequality for order of H. This will be order of G minus order of H, and if you do the simple calculation, you will see that order of H must be less than 1/4 the order of G, because order of G minus 3/4 of order of G will be greater than order of H. So you get this. Okay. Now we will go through some arguments which we have to see and understand carefully. Choose some element H belonging to G minus H minus identity. We are choosing some element H that is not in capital H, at the same time that is different from the identity. That is clearly possible. The question is this possible? Is this choice possible? It's clearly possible, because you see order of H is less than 1/4 of the order of G. So whatever the case may be, you can always choose some element in G that is neither in H and nor is equal to the identity element. In other words, you can choose an element from G that is different from the identity and is not in H. Okay. Now for any element K belonging to that same set satisfying KH not equal to HK. If there is some such element K that does not commute with H, this H, then what happens? HKT is equal to what? Note that because T is a homomorphism, it's an automorphism means it's a homomorphism, so HKT will be HTKT. Now neither H nor K belongs to H, so that means both of them will be mapped by T onto their inverses, because that's exactly something that does not happen in H. So since these are outside H, so that thing will happen. So that means this will be H inverse and this will be K inverse, and that is equal to KH inverse. And because of the way we have chosen K and H, this is not equal to HK inverse. So that means HK is a group element whose T image is not equal to its inverse. So HK belongs to H. This implies HK belongs to H. Okay, now the conclusion is this. By the cancellation laws, different such K in G minus H minus E will produce different HKs in H. What are we saying here? This is say our G minus H minus E, and say this is H. We have chosen some element H here and we have kept it fixed. Now for any K belonging to this, for which HK is not equal to KH, we are getting an element HK in H. You take another K, say K prime, that also satisfies this. you get another such element hk prime in H. And why we are saying that distinct case give us distinct elements, that is coming from the cancellation clause, because if these two are equal by the by the left cancellation law, k must be equal to k prime. So the more you get k's, different k's here in this set, for which none of them commutes with H, then you will keep getting different elements in H. But this clearly has an upper limit, because our group is finite, and as such the subset H is also finite. H has order of H elements. So correspondingly, there should be a restriction on the number of such cases that can be chosen for which this thing will happen. Okay, and that restriction clearly is this. So you can choose at most this many cases in this set such that they do not commute with H. So we are now going to write these things. Since H has order of H elements, this implies that we can get at most order of H elements k belonging to G minus H minus E such that it does not commute with H. Or equivalently, we can get at least, is this how this is supposed to go? Okay, but before we write the at least part, there is something else. Till this, there is no problem. Since order of G minus H minus E is equal to order of G minus H minus 1. This one is coming because of this, of course. And so that means if we subtract the order of H from this, yeah, that's what we should calculate. If we subtract the order of H from this, then this becomes equal to order of G minus H minus 1, which is this minus order of h. Now order of g minus h is greater than this minus 1. This is less than minus 1 by 1/4 of the order of g. So minus of this will be greater than minus 1/4 of the order of g, and this expression now becomes 2 divided by 4, that is 1/2 of the order of g minus 1. Okay, so let us now go back to the previous line. Since h has order of h elements, so we can get at most that many elements k here that do not commute with h. So that means I am also getting confused. At most this many elements for which something happens. So at least that many elements for which this does not happen. Okay, so since this is equal to this, there are at least m elements k belonging to g minus h minus e such that hk is equal to kh, where let us now see this final part. Since h has at most these elements, h has equal to order of h elements, this implies that we can get at most this many elements k for which, let us denote the number of elements k in G for which this happens by something. Let that be alpha. Alpha denotes the number of elements in G minus H minus E that do not commute with K. So this line is saying that this alpha is at most order of H, that is alpha is less than or equal to order of H. Okay. So for this many elements this happens. For the rest of them this will not happen. Rest of them means which ones? Namely the other elements in G. Well, not exactly in G but here, because it's from this set that we are choosing K. So for this many elements K in this set, this happens. For the remaining elements, what will be the number of the remaining elements? That number will be this. minus alpha. For these many elements in this set, they commute with with h, and this is greater than or equal to minus order of h. This is m. Okay, and we have proved that this difference is greater than half of order of g minus 1. So that's why m is greater than half of order of g minus 1. Now it is clear. If you want, you can write like this also. You take assume that alpha is the number of elements, so that you don't have to use words like this, number of elements, at most and at least. You will get confused using only, if you use only words. But if you can turn them into inequalities, then you can use your usual rules of inequalities, so that you don't make a mistake. Anyway, so now this. So what are we saying now? There are at least m elements in this set that commute with h, and we have a lower bound for m. Note that in this set e is not there because we have removed e, but e also definitely commutes with h. Thus, there are at least m plus 1 elements in g minus h, elements k in g minus h, such that kh is equal to hk, and in brackets you write. We are now counting E2. Now what does this final line mean? It means that the number of elements in the group that commute with that element h is at least m plus 1. Actually, since we are considering elements from g minus h, we are not considering all the elements of g that may commute with small h. But okay, there may be more elements, but at least m plus 1 are there. This implies that the order of the normalizer of h, if you recall, the normalizer of h, element h, is the set of those elements in the group that commute with h, and we have proved that this is a subgroup of any group. So this normalizer must be greater than or equal to m plus 1, and m plus 1 is greater than 1/2 of g, because m is greater than 1/2 of g minus 1. So these m plus 1 elements that commute with h we have got in g minus h. There may be more, so that's why we have inequality, and this is greater than this. So n of h is a subgroup of G satisfying this. Or 2 is greater than order of G divided by order of NH. By Lagrange's theorem, order of G divided by order of N of H is a positive integer. Because any subgroup divides the order of a finite group. So what does this inequality tell us? It tells us that this quotient must be equal to 1. And hence G must be equal to, so the orders should be equal, and because NH is a subset of G and G is finite, so the sets themselves must be equal. Now this tells us that every element of G, the normalizer of small h, is the entire group. That means all the elements in the group commute with H. This now implies that H belongs to the center of G, because H commutes with all the elements of G. So far there is no problem. There is only one confusion that I am having. It's about the ability to choose this H. Can I always choose this H? If not, then that means this set must be empty, in which case G must be equal to H union E. Now the hypothesis of the exercise says that more than 3/4 of the elements of G of the elements of G are mapped onto their inverses. No element in H is mapped by T onto its inverse. That is the definition of H. This is the only element which is mapped by H. Okay. So that means in this particular case, the number of elements that are mapped by T onto their inverses is exactly 1, this element only, and according to the hypothesis, this should be greater than this, or 4 divided by 3 should be greater than order of G. Now 4 by 3 is 1 point something, so that means order of G should be equal to 1. If we are unable to choose this H, then order of G should be equal to 1. That is, G should be the trivial group consisting of only one element. So in the beginning itself we have said that G is the non-trivial group, so that's why H can be chosen. Okay, fine, no problem. In fact, to make matters much more clear, before choosing H, you can give this small argument also, that actually there exists an H. Okay, so now so what do we have now? Note that although we chose H in the beginning from G minus H minus E, and we then kept it fixed and we then worked with K, but this H was arbitrarily chosen, since H belonging to G minus H minus E is arbitrary. We have, and all such H are being shown to be in the center of G. So the order of the center of G must be greater than or equal to this. Is greater than or equal to and this thing is greater than 3/4 of the order of G minus 1. And keep in mind that the way we have chosen H is not equal to the identity. So if we now take into account the identity also, or in fact we can actually, instead of writing this separately, we can write it at once. Since H belonging to this is arbitrary, we have this plus 1, because the estimate that we are getting from the elements H here, that is this. Additionally, there is the identity element also in Z of G, so that's why we are putting plus 1, and this is order of G minus H minus 1 plus 1 which is order of G minus H, and which by our hypothesis is greater than 3/4 of the order of G. Now you can again apply Lagrange's theorem and conclude that Z of G is equal to G. So arguing like above, thus G is abelian. Okay, so we have proved one part of the exercise, namely that the group is abelian, but there is still something else. We need to now show that T actually maps every element onto its inverse, or in other words, we need to show that this H is empty. Next, we claim that G minus H is a subgroup of G. For this to be a subgroup, first of all, it should be non-empty. It is non-empty because E belongs to G minus H. Why? H is the set of those elements that are mapped by T onto some element that is not the inverse of that element. E is clearly mapped by T onto E, and E is its own inverse, so E cannot be in H, so that means E must be in G minus H. For G1 and G2 belonging to G minus H, we have G1, G2, T, because T is a homomorphism, G1T, G2T, because none of these belongs to H, so both of these things are the inverses. Which in the group is G2, G1 inverse, but we have just now proved that the group is abelian, so this is G1, G2 inverse. So we see that G1, G2 is an element in the group which gets mapped by T onto its inverse. So G1, G2 cannot be in H, so that means it must be in G minus H. Thus, also, but we are in a finite group, no? So this much is enough to conclude that G minus H is a subgroup. Thus, is a subgroup of G. Now, since we already have an estimate of its order, it's greater than 3/4 of the order of G. Yes. Again, like before, applying Lagrange's theorem, G must be equal to G minus H, but then H must be empty. This implies H is empty, and hence xt is equal to x inverse for all elements x belonging to G. So if an automorphism maps more than 3/4 of its elements onto their inverses, then it has to map all the elements onto their inverses, and hence the group must be abelian. Although that is not the order in which we proved the thing. We first got the fact that the group is abelian, and then we proved that T maps all the elements onto their inverses. Now, an exercise related to this one. In exercise 12, can you find an example of a finite group which is non-abelian and which has an automorphism that maps exactly 3/4 of the elements of G onto their inverses. Okay, so the previous exercise says that if the mapping takes the elements onto their inverses more than 3/4, then the group must be abelian. However, can we find an example where this happens for exactly 3/4 of the elements and the group does not become abelian, it stays non-abelian? And it turns out that there is such an example, which proves that this 3/4 thing is a sharp bound. It has to be more than 3/4, otherwise commutativity is not guaranteed. Now the problem with this solution is that it's a group that we will encounter or see much later in group theory. Although in rings we have actually already come across the group that we are now going to present here as an example. It's the group of quaternion units. Let me just first write the solution and then we will understand all of its aspects. Where a square, b square and c square, all of them are theta. So here again this is something that I have taken from one of the exercises that is yet to come in a section that is yet to come in group theory itself. But what I am saying here is that again Herstein is using presentation of groups to say something about this group. If any of us is an expert group theory, then these are not problems at all. I mean, whether a group is given using one of its presentations or whether it's given using a set and a binary operation, but we are just students who are learning these things, trying to learn these things for the first time. So how are we supposed to know if there is even a thing known as presentation of groups, especially when it's not given in the text? Theta CB is A and CA is equal to theta AC is equal to D, and for this see exercise 21 of section, the 10th section of this chapter. We know, in fact, in that exercise we are asked to show that this is a non-abelian group. So from there we know that G is non-abelian. We are now going to define an automorphism. Et is E, theta t is theta, AT is A theta, Okay. Theta AT is A, BT is B theta, theta BT is B. Defining it means we have to say what the image of every element under the function is. That's what we are doing. And then CT is C and theta CT is defined to be theta C. One can, these are the really bad places. One can means I have and you are supposed to. One can verify that T is an automorphism. Warning, it's tedious. You have to do a lot of calculations. But if you persevere, you will see that it's actually an automorphism of this group. It is tedious because you see the group has 8 elements. So if you take any 2 of them and then verify that the function P satisfies the condition for a homomorphism, there are many, right? So you have to go through all of them actually. And since the group itself is pretty unknown, so we don't know whether it has any symmetry, whether if you think of it, there are symmetries, of course. For example, A, B and C behave equally. They are just like any one of them is like the other two. So by using such symmetries, you can cut down on the number of calculations, but you have to be careful. You should know exactly what you are doing. Anyway, one can prove that it's an automorphism, that is T is in A of G. Also, we can see that T maps exactly 6 elements onto their inverses. E, of course, is one such element. Theta is one such element. A gets mapped onto A theta, and it turns out that A and A theta are inverses of each other. 1, 2, 3. P gets mapped onto B theta, and wait, am I missing something, or have I made a mistake? What are the, wait, I think A and A theta are not inverses of each other. What do we get when we take the product of A and A theta? Let's just see for a moment. When we take the product of A and A theta, then we get A square theta. Okay. Now A square is theta, so that means we get theta square and theta square. Yes, So this is true. So that means this one they get mapped onto their inverses. Just like that, B and B theta, I mean theta B or B theta, you will see if you go through the calculations of this group that theta B and B theta are actually equal. Theta commutes with the other elements. So A gets mapped onto its inverse A theta gets mapped onto its inverse A, B gets mapped onto its inverse B theta, and B theta or theta B gets mapped onto its inverse B. 4 elements, and E gets mapped onto E, inverse of E is E, and theta gets mapped onto theta, inverse of theta is theta. But C is not the inverse of C, because C square is theta and theta is not equal to E. Like that, theta C is not the inverse of theta C. So exactly these elements are mapped onto their inverses. Theta A, B, theta B. Exactly 6 of them. And six is 3/4 of 8. Now, if you already know about the group of quaternion units, then this is nothing but that group. In fact, it's just that same group written in using different symbols than the usual ones. In the ring of quaternions, there are, of course, real quaternions. It's a division ring, so any non-zero element has an inverse, but the quaternion units don't mean units in that ring. Okay, quaternion units are these. If one restricts the multiplication operation of the ring of quaternions on this set, then it becomes a group, and E here is actually 1 and theta is -1, and this A, B and C are I, J and K. So theta A, theta B and theta C are -I, -J and -K. That's just the thing. So this is a group where there is an automorphism that maps exactly 3/4 of the elements onto their inverses, and the group is non-abelian. And finally, let us solve another one. Prove that every finite group having more than two elements. Oh, and this tediousness of the calculation is a first-hand experience. Okay, I am not just simply writing it's tedious just for the sake of writing it. I have actually gone through all the things. It took quite a while, means I think it took 1 or 2 hours every day for 3 days to carefully and slowly go through all the things. If you want, you can go through it, but if you feel that there is no need to do that, you can take my word for it, then you can just leave it right like this. Having more than 2 elements has a non-trivial You may be able to perform this calculation somewhat faster than me, because my thinking is extremely slow. So now we are given a finite group. It's the only thing that is given is that the group has more than 2 elements. So we now have to prove that it has at least one non-trivial automorphism. Now this thing we have already seen in the text. In the text, we have already produced non-trivial automorphisms of a group G if G is non-abelian. The inner automorphisms in that case have shown us that we can have non-trivial automorphism. Or if G is abelian with at least one element A satisfying A square not equal to E. Okay. So now we assume that G is abelian and G square is equal to E for all G belonging to G. So now G is a finite abelian group in which the square of every element is equal to the identity. And at this point one can, if one wants, one also can avoid the structured theorem for finite abelian groups. But I don't really know if one avoids this theorem, which is actually in the last section of group theory in this text. How one can come up with a solution, I don't know that. So we are going to prematurely use the fundamental theorem of abelian groups by maybe there is no way around using this theorem. That's why there is a star in this exercise, that we need more advanced knowledge of group theory to solve this exercise than what we have so far. By theorem 214.1 from the 14th chapter, we have any finite abelian group is a direct product of cyclic groups. What this Cartesian or how this Cartesian product is a group, you will get that in the 13th chapter, where we will see direct product of groups. So this solution also, just like this one, you have to just take it and keep it. After we have gathered the necessary things to be able to understand them, we have to come back to these things and then properly understand them, or rather you have to come back to these things. Okay, I may by that time I may forget the things, but for now you keep the things with you. You have the solution, its understanding has to wait. Where Hi is a cyclic group, or each Hi is a cyclic group. We can of course assume without loss of generality that none of the Hi's is the trivial group. Since every non-identity element by our assumption in G has order 2, Hi is isomorphic to J2 or Z2 for all the indices. Thus, G is isomorphic to J2n, which is the direct product of n copies of J2. Now that we have a concrete group with us, we now know that G is essentially this. So we can now show that there is a non-trivial automorphism, and that automorphism is this. A2, A1, A3. So this automorphism interchanges the first and second coordinates of this of any n tuple coming from here. It's straightforward to verify that F is an automorphism of, I need more ink. Also, this automorphism is non-trivial. Because n is at least 2. Here the solution ends. Clearly, this part cannot be understood just like that, because we don't know what these things are. So if we take these things to be true, that is, if we assume that yes, okay, we come to a stage where one can show that G is isomorphic to this group, then one can define a function like this. It will be straightforward to verify that this F is an automorphism of this group, and it's a non-trivial automorphism because it does not map every element onto itself. and that is because of the switching of the first and second coordinates. And we are writing this is non-trivial because n is greater than or equal to 2. The number of copies of J2 we have in this direct product is at least 2. That's why this automorphism is non-trivial. Since we cannot have a full understanding of this solution right now, so we keep this part also like this, but at least we can understand one thing. n cannot be 1. If n is 1, then G becomes isomorphic to J2, and J2 has only 2 elements, 0 and 1, but it's given that G has more than 2 elements, so that's why the things fall in place. So we keep the solution like this. We will come back to it, and I stop the video here itself. Tomorrow there is what? Calculus, and in next week instead of now group theory will go on like this. I am thinking of starting something else. Will this be the perfect time? No, it's not. It won't even be a good time to start differential equations. We can, but we want to do the things somewhat rigorously, more rigorously than they are usually done. So we will have to wait until we get to the chapter on differentiation, at least in Tau's analysis. Then we will start differential equations, both ordinary first, and then partial. Okay, so that's just it. That will be all for tonight. So see you tomorrow. Until then, it's me, Lucifer, from a mathematical room. Have a nice night.